Hi everyone, welcome back to a continuation regarding enthalpy changes. So previously we looked at Hess's law in part A to this, and that was, as we had mentioned, a way of theoretically determining enthalpy and molar enthalpy when we don't have calorimetry data. So we can use the balanced equation and intermediate steps to determine what a target equation's enthalpy change will be. So in part B, which is this video here, we're going to look at scenarios where we don't have the intermediate steps that make up that overall reaction. So we're going to look at how can we just determine the energy change based on the substances that are present, and there's a way for that using reference data. So our goal here, again, is the same as before: determine enthalpy changes without a calorimeter. Right? We're going to learn about what enthalpies of formations are and how they can be used to find the change in enthalpy. And then we'll use those values to solve problems and understand the impact of the energy sector in trying to fine-tune the energy production and consumption of reactions with the environmental and social impacts. So just because we can get a lot of energy out of a substance doesn't mean that it's necessarily safe to use, nor are the ethics behind obtaining that substance necessarily clean. Okay, so we'll talk about it at the end. So to start off here, we're going to define enthalpy as a state function. So what does that mean? It doesn't depend on its history. So whether we use 2 intermediate steps or 5 intermediate steps, the overall enthalpy change will be the same. So if we have our target equation, okay, there's a variety of intermediate steps we can do. So let's say we have A and B, which each have their own enthalpy change. And then a second way suggests A, B, C, and D. Well, no matter what happens, when we add all of these up together, the overall energy change will be the same. And that's what a state function is. It's just saying comparing the beginning and the end. All right, and all the steps in the middle aren't, not that they're not important, they cancel each other out in terms of the impact on the overall function. So when we had the intermediate steps, we were using full reactions, 2 or 3 of them, that added up to the target equation. Now we're going to use more than that. We're going to use more simple equations, but it'll still give us the same change in the end. And that's what state function is defined as. There's more than one way to determine the final product. So we're going to use a technique and a property, not a technique, called enthalpies of formation. So there's a couple of things here. Number one, delta H represents enthalpy. The F represents formation, right? And because it's a reaction, that means it's going to be in kilojoules per mole. And then lastly, the little degree sign here means standard conditions. Okay, and we learned about standard conditions in an earlier course, grade 11 chemistry. Standard conditions are generally 25 degrees Celsius and 100 kilopascals atmospheric pressure. Those won't factor into our reactions, but just to understand how they were determined in the first place. So an enthalpy of formation, right, is described as this second bullet point here: the change in enthalpy needed to form 1 mole of a compound from an element in their standard state. Right? Now, in terms of an element themselves, their formation enthalpy is 0 because they are formed in nature. There's no process that goes on past that. So we say it takes no energy to form something that we can find because it's there. So what does this mean? An example down here, what you see is the formation equation for water. So water is made up of, if we just draw its structure even to see it here, made up of hydrogen and oxygen. So a formation equation says that hydrogen plus oxygen produces liquid water, and everything's in their state from the periodic table. All right, so we'll be careful to pay attention to that. So in your textbooks on page 320, and there's so many reference sheets about this on the internet as well. You can see a posted one for more details. You'll see standard values, and that'll tell you the energy change associated with these formation equations. So let's do an example. From this page here, I'm going to look at aluminum chloride, which is listed as a solid. So to write a formation equation for that, I just look at the elements that make it up. So in this case, it's aluminum, which is a solid on the periodic table, and chlorine gas. Right? Those two combined form aluminum chloride. Now, the enthalpy change associated with this is negative 704 kilojoules per mole. All right, so that's the formation enthalpy, which means it's an exothermic process. Now, when we balance this, and I'll just do that quickly. You can pause if you'd like to try it yourself. Okay. Notice how there's a 2 in front of the aluminum chloride. So this formation enthalpy always describes the compound being formed. Okay. So in reality, if we were to do this reaction, 2 moles are being formed, so double the amount of energy would be released. But we keep it in terms of kilojoules per mole so that we can apply it to other scenarios. So by doing one of these reactions for every single compound in a reaction, what you've done is essentially generated the intermediate steps. Now you've generated a lot more than we did with Hess's law, but what we said is that it'll give you the same outcome. Okay, so now we don't need to rely on reactions that have already been studied. We can rely on compound data, which is a little bit more available to us. So mathematically, what do we do with that now is the key question, because this helps us to determine one substance. And the question is, well, how do we figure out a more complex reaction? So in Hess's law, we added the enthalpy value for each individual step. Now we're going to do the same thing here, only we're going to expand on it a little bit so that we don't have to rearrange those. Okay. If we follow the equation in the box, the sum of the enthalpy of formation of the products minus the enthalpy of formation of the reactants, that will take into account all the flipping and rearranging that we've done and let us skip it. So this is like a one-step mathematical application. So these enthalpy of formation values come from the chart on page 320. Okay, so you'll need that as reference. And it's important to know you don't see any elements on that chart because their values are 0. So any element in its standard state is 0. I'll give you an example of that. Bromine is Br2 and it's in a liquid state. So its enthalpy of formation is 0. The only other liquid on the periodic table is mercury. So it's also going to have an enthalpy of 0. If you ever see a liquid for any other element, it will have an enthalpy of formation because it's not naturally found like that. Okay. Now keep in mind we're finding the enthalpy change when we don't have calorimetry data, so no temperature, right? We haven't found a change in temperature, or we weren't given intermediate steps, so we're kind of creating our own. So this equation is key in terms of energy production and analysis. So let's apply an example to it. We'll go to Word document for a bit more room here. So the question is simple. What's the enthalpy of combustion of methane fuel? Right? And that's all we're told. We're given the reaction for it. So the enthalpy of combustion would be delta H combustion. Okay. So to figure that out, we need to know the enthalpy change and the number of moles. So based on the information we're given, the number of moles comes from the coefficient, and the enthalpy change comes from adding up the enthalpies of formation. So let's start off by balancing this, and you can always pause and try this yourself before you come back and check the answer. I'm going to do this quickly. Okay, so put a 2 in front of those there. Now, we know for methane, there's a coefficient of 1. So that means there's 1 mole in this reaction. For the enthalpies of formation, okay, we'll use delta H, the sum of the enthalpy of formation of the products minus the sum enthalpy of formation of the reactants. So here's how we're going to structure that. And these values come from page 320, right? Or you can search up a chart to download for yourself, or you can print off the one that will be on D2L, okay, in the reference data section. So we'll go here, just kind of while I pull up the numbers here to have with me. Okay, and it's reference data, we don't need to memorize that. So we're going to open up a square bracket because this symbol here means add all of the values for the products. It means the sum of. So we'll start off with each product individually. So we'll make a bracket for each one. So I have 1 mole of carbon dioxide based on the balanced chemical equation. Now in the chart, its enthalpy of formation is 393 kilojoules per mole. So that's how much energy is going to be released from forming 1 mole of CO2. Now I'm going to add to that 2 moles of H2O, and it's important the state. Okay, it's gaseous water here, because if you look on that chart, there's 2 different values. So in this case, it's negative 241.8 kilojoules per mole, not negative 282. Okay, and now that's all of my products, so I'm going to close that bracket. And you see that it means everything inside this bracket is a product, and I will add that together. Then I'm going to open up a second bracket to subtract the reactants. So I'll start off with 1 mole of methane, and its formation value is 74.4 negative kilojoules per mole. And then my other substance is oxygen. Now, if you pause for a second and try to find oxygen on the chart, you won't. I want you to think about why. Okay, if you've paused and thought about it, good. You should be thinking that, well, oxygen's an element, so its enthalpy of formation is 0. Okay, so it won't be added to there. So that's it. That's all the data we need to determine the enthalpy change. We'll simplify it by saying, we'll look at the products change first. 0.1 kilojoules, and notice how the moles went away. Take away negative 74.4, so you're just evaluating each square bracket. Right? And the square brackets tell us to work within those first and then simplify this step. So we get an enthalpy change of negative 802.7 kilojoules. Okay. Now we'll have to keep in mind this is, as per the coefficients, 1 mole of CH4. Right, so our molar enthalpy of combustion is going to be delta H over N CH4. And we have no other data here, so this is what we're using. And we'll get negative 802.7 kilojoules per mole of methane. So no matter what reaction we carry out now, we know that every mole of methane that reacts releases 802.7 kilojoules. So now if we have a specific amount, we could go ahead and apply that to it, and we'll do that in the second one. So the enthalpies of formation allow us to determine the molar enthalpy of a specific substance and then use that in a real-world application or with a different amount. So the number of moles here comes from the balanced chemical equation, giving us the molar enthalpy. Okay, and we'll do this for substances we don't know, and it'll allow us to determine the amount of energy they release. So we'll do another example now. We're going to take it one step further. Determine the heat produced when 2.55 kilograms of CO2 is formed in the combustion of acetone. So just to save some space here, I'm going to write the equation up here. So we'll go with the short version of the equation here. Combustion is by combining it with oxygen, and it forms gaseous CO2 and gaseous water. That's important. Okay, and the reason it's important is because water has a different enthalpy of formation based on the state. So if we balance the carbon first, we'll have 3 there. We'll have a 3 in front of the water. And then we'll have 6 and 9. We'll put a 4 in front of there. So there's our coefficients. So to figure that out, right, the amount of heat, it's going to be the number of moles times the molar enthalpy. Okay, so we had said before, the number of moles can be written as mass divided by molar mass. And the molar enthalpy can be determined with just a balanced equation and the enthalpies of formation. So let's try that here. So we'll start with that. Delta H is equal to the sum. So anytime we need to determine an energy change without data, we can use these enthalpies of formation. Product, and again, the degree sign tells us the conditions they were determined at. So we have our balanced equation. We'll start with a square bracket. There's 3 moles of CO2. And again, these values come from the chart on page 320. plus 3 moles of water. Okay, and again, make sure you're looking at water in the gas state. Okay, we only have 2 products, so we'll close the bracket there. The value for acetone is given here, and sometimes if it's not given, then or if it's not in the chart, we'll give you that. We'll have some reference data. 247.48 kilojoules per mole. And all I'm going to rate here is plus 0. See if you can remember why. Okay, and hopefully you thought that that's because, well, oxygen's an element, right? So it's nothing, there's no energy change. So then when we simplify each one of those brackets, we're going to get 1905.9 kilojoules. Take away bracket negative 247.48 kilojoules. Again, we simplified out the moles. We get an energy change of negative 1658.42. So I'm just keeping some significant digits extra as we go through this. So there's the energy change. Now we had said the next step for this is to turn that into a molar enthalpy value. So delta HR is equal that. So because we're working with CO2, that's the number of moles that we're looking at. So there's this much energy released as per the equation when 3 moles of CO2 react. Okay, so I'm going to squeeze this down here. So when you simplify that, it's going to be negative 552.8 kilojoules per mole of CO2. Right. So that's the benefit of using the enthalpies of formation. Okay, without any lab data, we can we can determine the molar enthalpy. And now in our final calculation, we can apply that to the amount that actually reacted to figure out the energy change for that amount. So moles times the molar enthalpy. Okay, we're given 2.55 kilograms, so mass divided by molar mass has to be in grams, 2,500. Molar mass of CO2, carbon is 12, each oxygen is 16, so that adds up to 44.01. We determine this value, okay, using Hess's law, and now when we simplify that, we're going to get about 32,000 kilojoules released during that combustion process. Okay, and that's our final answer. So to combine everything we've been working with, Hess's law allows us to determine an energy change, so do the enthalpies of formation, similar to everything we've done. And then we can apply that once we know a molar enthalpy to any amount for those substances. So we'll stop it at that point with those 2 examples. We'll do a part C for example number 3 because it is complex and it combines quite a few more concepts into it. Right, if I go back to the PowerPoint here, right, we'll start off by differentiating, we'll end off by differentiating between enthalpy and molar enthalpy. Okay, so make sure we understand what the values represent. We find delta H from Hess's law and the variance, and then we divide it by the coefficient to determine the molar enthalpy. Okay, so Hess's law does not help us determine the molar enthalpy. We determine it using the coefficients at the end. Right, and if I go back to here, that's like, just to highlight it in a different color, the step that we did here. So Hess's law gave us the energy change. We divided by the number of moles in the reaction to get the molar enthalpy. Okay, so we'll come back for part C to do this example here. It's a big one, so we'll dedicate its own video to it. And I hope that helps clear a little bit more up.